Welcome to another lecture on fluid mechanics. In this lecture, we will do some problems related to viscosity of fluids. So, in previous lectures, we have seen what is a viscosity, how it is defined, and for a Newtonian fluid, tau equal to mu du by dy, that is the Newton's law of viscosity applicable to Newtonian fluids, that also we have seen. And what is the effect of viscosity, that is development of shear stress. So, this viscosity relation we have studied, and we have seen the viscosity values of various fluids, how it varies with temperature, and what is the reason for variation of viscosity of liquids as well as gases with temperature, etc. we have seen. And now we are going to do some numericals based on essentially based on Newton's law of viscosity, that is tau equal to mu du by dy. So, we have three problems on viscosity, and before that we will do a problem related to the fundamentals of pressure estimation. First problem is like this: calculate the specific volume in liters per gram of Jatropha oil sample having specific gravity 0.92. So, this problem will give you better understanding on the concept of or what do you mean by specific volume, what is density, what is specific gravity, etc. We know that. What is the problem? Let us see. The specific volume in liters per second of Jatropha oil having a specific gravity of 0.92. You see this? Specific gravity is what? Specific gravity, as we know, it is relative density. The given data is relative density of Jatropha oil as 0.92. Okay. So, what is the density? How to estimate the density? Because relative density is the density of Jatropha oil divided by water. So, the density, absolute density is 0.92 into density of water. That will give you 920 kilogram per meter cube. That is very simple. Okay. So, we got the mass density as 920. Okay. Then we want to find out specific volume. So, what is specific volume? As per definition, it is volume of unit mass. Volume of unit mass. So, what is that? Volume by mass, or that is reciprocal of mass density. Density is mass by volume. So, 1 by mass density, 1 by 920 meter cube per kilogram. So, 1 by 920 meter cube per kilogram. You need the value in liters per gram. So, 1 meter is 1000 liters. So, how to do that? 120 multiplied by 1000 divided by 1000. That is, you need in 1 kilogram is 1000 kilograms, sorry, 1000 grams. So, multiplied by 1000 in the numerator as well as multiplied by 1000 in the denominator. That give you the value of 0.001 liters per gram of Jatropha oil. That is a specific volume of Jatropha. Now, that is regarding the pressure sorry, that is regarding the basic properties of fluids. I'm sorry, not regarding pressure, that is regarding the basic properties such as mass density, etc. Now we will do a typical problem in viscosity. The problem is like this: in a stream of glycerin in motion, at a certain point the velocity gradient is 0.25 meter per second. Velocity gradient. If for the fluid the density is 1268 kilogram per meter cube and the kinematic viscosity is 6.3 into 10 raised to minus 4 meter square per second, calculate the shear stress at the point. Okay, what is that? Given data you can write. It is asked for KTU July 2017 examination. What is that? Velocity gradient is given as 0.25 per second, that is du by dy, 1 by second, or second raised to minus 1 is a unit. Then density is given as 1268. Okay. Kinematic viscosity is given as 6.3 into 10 raised to minus 4. SI unit is meter square per second. We need to find out shear stress. So, as per Newton's law of viscosity, we assume that glycerin fluid liquid is obeying Newton's law of viscosity. So, assuming glycerin is Newtonian in nature, we can write tau equal to mu into du by dy. Okay. Du by dy is directly given 0.25 by second, 0.25 per second. Then how to get mu, that is dynamic viscosity? We know that kinematic viscosity is dynamic viscosity divided by mass density. So kinematic viscosity is given and density is given, so you can find out the dynamic viscosity mu as nu into rho. So you substitute, instead of mu you can substitute nu rho into du by dy. So nu is 6.3 10 raised to minus 4 into 1268 into 0.25. The answer is 0.199 Pascal or Newton per meter square. This is very simple because directly it is given, velocity gradient as well as viscosities are given, so you can directly do that. Okay, we'll move to the next problem. You see this, it goes like this. Dynamic viscosity of oil used for lubrication between a shaft, that is a journal, and bearing is 6 points. So this problem is related to journal bearing. In a journal bearing you have a journal or the shaft rotating inside the bearing, and in between the journal as well as bearing you have a fluid film or highly viscous fluid film. The shaft is of diameter 400 mm, that is 0.4 meters, and it rotates 190 rpm, that is rotational speed of the journal is 190 rpm. So if you are given the rotational speed n, you can find out the velocity, that is the tangential velocity of rotation. Okay, calculate the power lost in the bearing for 90 millimeter long journal bearing arrangement. Thickness of the oil is 1.5 millimeter. Okay, so if you are given such a problem, you should understand that you have the viscosity value here, so you need to find out the power lost. Power loss means you have to find out the power lost due to viscous action. So it is a problem related to Newton's law of viscosity application. So you have to draw the arrangement first. So this is the arrangement. You see, this is drawn not to scale. You see this. This is a shaft which is rotating at 190 rpm. What is the diameter of the shaft? It is given as 0.4, rotating at 190 rpm. It is also shown here. And what is the length of the bearing? 0.09 meters, because it is 90 millimeter or 0.09 meter given. And we have an oil film. Thickness of the oil film, it is given as 1.5 millimeter or 1.5 into 10 raised to minus 3 meter. This thickness is, you read it as 1.5 into 10 raised to minus 3 millimeter, that is our dy. Okay, then what else? Okay, then we need to find out the power lost. So while this journal is rotating inside, what happens to this fluid film, oil film? So shear stress is developed in the oil film. Okay, so what about the velocity here at the surface of the bearing? Because bearing is stationary, the velocity is 0. Okay, so what about the velocity on of the layer of fluid that is adjacent to the journal bearing external surface? It is having a velocity, and that velocity will be the tangential velocity of rotation of the journal bearing. Correct. So you have the velocity 0 at the bearing surface, and you have velocity as the tangential velocity of rotation of the journal for the fluid layer that is sticking the exterior surface of the journal journal. Okay, so how to get the tangential velocity? Okay, we'll see that. So assuming the oil is Newtonian, you get tau equal to mu into du by dy. So mu as oil. What is du? So dy is, what is dy? It is a small thickness of the oil film, that is designated as small t. And what is du? Du, you see the previous case, it is the difference in velocity between the two surfaces of this thick oil film. So this is stationary, velocity of the bearing layer is stationary, so only velocity is the tangential velocity of the journal. That is, you can estimate the tangential velocity of rotation of the journal as pi dn by 60, where n is a rotational rpm, d is the diameter of the journal bearing, that is also given. So you can write mu of oil into pi dn by 60, that is the tangential velocity, divided by thickness of oil film, that is t. Okay, now this is the shear stress developed due to the rotation of the journal in the oil film. So it creates, we know the theory, it creates a viscous resistance. What is the viscous resistive force? Viscous resistive force R is equal to the shear stress multiplied by shearing area. You should understand this. Shear stress multiplied by shearing area. What is the shearing area? Because the oil is sticking the external surface of the journal bearing of diameter d and length l. So what is the exterior shearing area? Pi dl or 2 pi rl. So R will be tau into pi dl. Okay, so instead of R, you can write mu du by dl, mu of oil into pi dn by 60 into t multiplied by pi dl. So what is the power lost? We need to estimate the power required to overcome the frictional resistance or power lost. So power equation, we know power is always viscous resistance into tangential velocity of rotation. So you should understand this. R, that is a viscous resistance, multiplied by U, that is a tangential velocity of rotation of the journal. So what you will get, instead of R you can write tau into pi dl. So here it is tau into pi dl. What is the tangential velocity? Pi dn by 60. So you get, instead of tau you substitute from here, that is mu, from here you can substitute, that is mu of oil pi dn by 60t into pi dl into pi dn by 60. You substitute the values like this. Okay, all the values are known. Mu is known, d is known, n is known, l is known, t is also known, that is thickness is also known. You will get power lost in watt is 715 watts. Power lost is 715. This is how you calculate. So you have to understand two things. One is, once shear stress is given, how to estimate the viscous resistance. That is always the shear stress into shearing area. Okay, shear stress into shearing area. Then power loss will be that viscous resistance to overcome multiplied by tangential velocity. Okay, we go to the last problem in this section. It goes like this. A rectangular solid block of base 0.3 meter square weighing 90 Newton, that is a weight mg, okay, is allowed to slide down an inclined surface making an angle of 30 degree with the horizontal, you know. So inclined surface making an angle of 30 degree with the horizontal. The surface of the plane is smeared, that means polished with, applied with a 3 mm thick layer of lubricating oil. That is, thickness of the lubricating oil is 3 mm and its viscosity is 8 points. 8 points viscosity, that is a commercial unit. So what is the SI unit? 8 into 0.1 Newton second per meter square, or 0.8. You need to get velocity with which the block slides down the surface, that is a terminal velocity. What is it actually? We will draw the figure first. You know, this is an inclined plane which makes an angle of 30 degree with the horizontal. You have a weight that is sliding down over this thick film of oil which is 3 mm thickness, that is given. Okay, so this is the arrangement. So W, weight of the block, that is 90 Newton, that is acting downwards like this. Okay, so you have a wedge like surface which makes 30 degree and it is coated with 3 mm thick fluid, and the block is sliding down. Why it is sliding down? It is sliding down because of the weight only. So it will attain a velocity gradually. So that velocity is designated as small u. Given data, you see, mu is given 0.8 Newton second per meter square, that is 8 into 0.1. Thickness T is equal to 3 mm, that is given, so it is 3 into 10 raised to minus 3 meter. Assuming oil is Newtonian, you can find out the shear stress. How? Tau equal to mu into du by dy. So what is du? This is the thickness of the oil film. So dy will be what? T. Okay, what is T? 3 mm. What is du there? Difference in velocity between the two ends of the oil film. So here it is stationary, where on the solid block, on the solid surface, the velocity is stationary. So velocity of layer that is adjacent to the block will be having the terminal velocity of the block itself. So that is u. Okay, here velocity is u here, and here velocity 0. So difference velocity will be u minus 0, that is u itself, and dy is the thickness t, u by t. So mu into u by t. Okay, and now you see this, we need to find out u. T is given, mu is also given. Okay, so how to get tau? Once you get tau, you can find out u. So how to get tau? Tau is the shear stress that is developed in the fluid film because of the downward movement of the block. So how to get tau? Tau will be the component of this W, because it is moving down only because of its own weight. So W, component of this W along the direction parallel to the surface, inclined surface. So W has to be resolved along this direction. How to resolve W along this direction? We know this angle. So how to do that? it is diagrammatically shown here. W, here it is acting down, this is 30. Okay, what is this? This is 60. So this will be W cos 60 or W sin 30. So W sin 30, that is 90 sin 30 will be the shear force in this direction. It is the shear force in this direction. Okay. Oh, so what about the shear stress? 90 shear force divided by shearing area. So what is the shearing area? You see this shearing area, it is given as 0.3 meter square. That is the block base area of this block. So 90 sin 30 divided by 0.3 will give you the shear stress. So tau equal to mu du by dy. This is tau, this is mu, u we need to calculate, dy is thickness of the oil film. Then substituting all these values, we get u as 1.11 meter per second. Thank you.